I want to welcome you all here on the first day of summer. So happy summer solstice, everyone, and happy Father's Day to those among you who are indeed fathers. And I want to say a couple of things. Today's talk is by Sam Courville, who's a PhD student in geology at ASU. He is the first, I've confirmed this with Juliet, he's the first graduate student that we've invited to give a talk at our lecture series. And there's a reason for that. In March at the Lunar and Planetary Science Conference, they had some pre-recorded talks, and Sam gave one. I think they were roughly half an hour or thereabouts. And I thought his talk was particularly insightful, cogent, and easy to understand on meteorite magnetism. Now, I've been interested and baffled by this subject since the early 80s, looking at some of the papers there by some of the notables at the time. This subject continues to come up in questions about whether asteroids have dynamos, whether not just differentiated asteroids, but some asteroids, some chondritic asteroids, which is a very controversial assertion that they may have dynamos. And so I thought it was important for everyone to be able to get a sort of elementary view of this particular topic. And I was impressed by Sam's presentation in March in Houston. So, sort of formal introduction, Sam Courville is a PhD student, geology at ASU. And he got his master's degree at the Colorado School of Mines and Geophysics. He's just been there, I think this is his first year, he told me. And I'm looking forward to this presentation, not just for my personal edification, but I think everybody will benefit by getting a grounding in this particular subject matter, because it comes up all the time in terms of the history of the solar nebula and the history and the geological petrogenesis of various kinds of meteorites and the history of their asteroids. So I'd like to introduce Sam. Please take it away.
Thanks so much for the introduction and for the praise. I'll do my best to live up to it here. Yeah, first day of summer. It's actually like 115 degrees out here in Tempe, so that's fun. I don't know if you guys have ever been to ASU, but we've also got a pretty cool meteorite collection. So, you know, if you're ever here, definitely stop by. But my talk today is I'm going to talk about the magnetization of meteorites and asteroids, and this is something that I'm starting my PhD research into. Oops, let me click, there we go. Right, so, I mean, you guys are all meteorite enthusiasts here, right? Rocks from space. I'm imagining, I would do a hand pull here, but this is over Zoom, so I'll just guess that some of you have been hunting for meteorites before. And if you have been hunting for meteorites before, maybe you brought along a magnet with you. You know, you could go out to like an open field or something and tow along a magnet and see what you pick up, because these like iron meteorites are very magnetic. You can, they're very attracted to a magnet. This isn't a foolproof method because there's lots of other rocks on Earth that are naturally magnetic. But you'll hear this a lot, that these meteorites are very magnetic. But at this point, I need to make a distinction between a material that is magnetic and a magnet itself. So basic, back to school, here's a basic cartoon of a bar magnet. It's got a north and a south pole, and then it generates its own magnetic field. And so it's the magnetic field that attracts other metallic magnetic objects toward the magnet. And so you can't actually see this magnetic field, but if you were to place a bar magnet on a piece of paper with some iron filings, the iron filings are magnetic, so they will be attracted to the magnet, and they'll follow these magnetic field lines. So just to drive this point home, I've got this little bar magnet here, and I've got this little bottle with a tiny iron meteorite in it, a tiny specimen from an iron meteorite. And the iron meteorite is nice and magnetic, so I can, it's attracted to the magnet. I've also got a screwdriver here made of steel, also iron. And it is also magnetic, so magnet's attracted to it. The magnet has a magnetic field, but the meteorite and the screwdriver don't, so they are not attracted to each other. They're just magnetic, not magnets. And so the point of this is that we have these meteorites, they're magnetic, but not magnets. Or are they? It actually turns out that some meteorites are themselves magnets. And what we mean by this is they have been magnetized at some point. Magnets don't just spontaneously come into existence. You have to magnetize a piece of metal to make it a magnet. And so this is a meteorite over at ASU, and someone took it and put it on a piece of paper with iron filings. And just like the bar magnet, it lined up some of the iron filings, and they arranged themselves with the magnetic field of that iron meteorite. So right, so we've got these. So so what, right? Magnets are pretty common. Why do we care if some meteorites are magnets? And that's because, like I said, magnets don't just spontaneously form. To make a magnet, you have to magnetize the object. So how does a meteorite become magnetized? So there's a bunch of different ways you can magnetize an object. Some are quite simple. So for example, if I take my screwdriver again and I take my bar magnet and I just move it up on the screwdriver, I don't know, like 10 times or so, just over the tip here. Just doing this will actually magnetize the screwdriver. So now the screwdriver is actually a magnet. So I have a tiny little nail. So now it's actually a magnet. But the point is, I had to magnetize it with another magnetic field. So what this means is that these meteorites they've experienced some sort of magnetic field in their lifetime. So now we can do science, right? Now we have an observation and we know something about the history that these meteorites have experienced. So now I've only been talking about iron meteorites so far, but let's do a quick pop quiz here. Again, I can't see you all, so I can't see what you think. But which types of meteorites can be magnetized? So at the most basic grouping, there are 3 flavors of meteorites. We've got irons, and stony meteorites. So which ones do you think can be magnetized? And it turns out all 3 of them can be. And you might be wondering, well, how's that? What's right? I thought it was the metal that's magnetized. Well, it turns out it's iron. Iron can be magnetized, and even these stony meteorites, these primitive chondritic meteorites, can contain 5 to 30% iron by weight. Right. So now we want to know, if these are being magnetized, where are they being magnetized? How is that happening? So sort of a key assumption here is that these meteorites are, they're coming from, for example, the surface of asteroids. So an impact dislodges these meteorites, then they're floating around in space for a little while before they eventually crash down on Earth. Now, not all meteorites are sourced from asteroids. There are definitely a few that are from the Moon, the Mars, and possibly Mercury or even Venus. But I'm not going to focus on those. I'm going to focus on the asteroids as the source of meteorites. So this is interesting because even though we have these magnetized meteorites, we actually haven't found for certain a magnetized asteroid yet. So that's kind of confusing because these meteorites had to be magnetized some point in their lifetime, and they spent most of their life on top of on an asteroid, presumably. So the big question of my talk is going to be why this is the So a brief outline of where I'm going to go with this. I'll start with a brief overview of the evolution of asteroids and meteorites. And then I'm going to talk about the possible magnetization processes that could occur to generate these magnetized meteorites. And then from there, I'll talk about, I'll really start getting to the question of why we haven't found a magnetized asteroid yet. And I'll talk about where we've gone and where we're going to send spacecraft in the future. All right, so starting with the evolution of asteroids and meteorites. So sort of at the beginning of the solar system, we have a lot of dust and small particles, chondrules, like the size of pebbles, coming together and forming these first objects in the solar system. And they form rather quickly, as the latest research suggests these form actually rather quickly, and they can get to sizes of 50 kilometers or more in a short time period compared to the age of the solar system. And so they grow and they get quite big, but these early asteroids, they still have a lot of these short-lived radioactive isotopes in them. They have radioactive elements in them left over from the material available as these objects are forming. And so these young asteroids undergo a lot of heating, and they heat up. And as they heat up, the rocks undergo a lot of mineral transformations, and then if it continues heating, they may even melt. And when melting occurs, then everything's a fluid, so we can start separating out elements and minerals from each other. So the densest fluids are going to fall to the center of the asteroid, and the less dense materials are going to go to the surface. So then that's what we call differentiation. And so this is what produces, so in this case, we'd end up with an asteroid with an iron core, and then some sort of mantle, and then a crust on top. So we like this. This is by no means the only explanation for the processes that asteroids have experienced, but we like this explanation because it fits with the meteorites we've collected. Chondrites, these chondritic stony meteorites, they appear very primitive. They're like, they're very primitive, and so they fit very well with these objects that maybe didn't undergo differentiation. Meanwhile, we have the iron meteorites and the stony iron meteorites, the iron meteorites fit well with coming from like the core of a differentiated body. These pallasites, which are a mix of these olivine crystals and iron, could come from like a core mantle boundary. And then these achondrites, these stony meteorites, would fit coming from like a crust of a differentiated body. So, as I said before, all of these can be found magnetized. So along this evolution path, each type of these meteorites are being exposed to a magnetic field somewhere. So I'm going to start with the chondrites here. How are they being exposed to a magnetic field? So now I'm going to go into part two, the possible magnetization processes, starting with chondrites. So first off, it's not all chondrites, but it's a bunch of them. So there's been remnant magnetization measured in LL chondrites, CM chondrites, CR chondrites, and CV chondrites. And there's actually some nuance to studying the magnetic fields in these magnetized meteorites, because they're not all magnetized the same way, which is curious. For example, in the LL chondrites, it's actually iron particles within the chondrules that are magnetized, Whereas in the CM chondrites, it's the iron minerals, the iron-bearing minerals in the matrix, the material in between the chondrules that are magnetized. So this is interesting, and there's a lot of there's explanations for why this happens, which gets into more detail than I'd like to go into now. But the key point is that because these are in minerals, we can actually date using radiogenic dating methods. We can date when these when we think the magnetization occurred, and so that happened likely about 1 to 5 million years after the formation of calcium aluminum inclusions, which for the purpose of this talk I'll call just the beginning of the solar system. Right, and the solar system is 4.5 billion years old, so this 1 to 5 million year range is very, very young. These were magnetized at like the beginning of the solar system, basically. So what was going on at the beginning of the solar system where these guys could be exposed to a strong magnetic field? You might be wondering, well, hey, the sun produces a magnetic field. Like even today, the sun has the solar wind, right? That's a magnetic field. It's actually not strong enough to magnetize anything. But in the past, when the sun was very young, it may have looked something like this dramatic conceptualized image here, but the young solar system was, there was a solar nebula. So the sun was surrounded by a giant cloud of gas, gas and dust. And this could sustain a much stronger magnetic field than the solar wind today. And asteroids were forming in this cloud. So the dust was coming together, forming these objects within this cloud, presumably within this magnetic field. So that's the prevailing explanation for these early magnetized chondrites. And so this is some great recent work from the paleomagnetic group at MIT that's tried to place all of these magnetized chondrites into a history of events for the solar nebula. And so on the bottom axis is the time, basically the time after the formation of the solar system. And on the vertical axis is the strength of the magnetic field. So they're deriving the strength of the solar nebular field from the remnant magnetization in these chondrites. And so what you get is that the LL chondrules and the CM chondrites are quite strongly magnetized, and they put limits on how weak the solar nebular field must have been. So we know there was quite a decently strong solar nebular field at this time from these meteorite paleomagnetic results. And this has raised new questions that maybe these strong magnetic fields were also a key part in bringing material together to form these bodies in the first place. That's been a long-standing speculation. Right, so these meteorites are forming in this nebular field, but they're actually part of asteroids at this point. It's not just the meteorite being magnetized, they're on asteroids. So these magnetized meteorites are placing constraints on what the early asteroids experienced. So for example, this is taking a sample of the Murchison meteorite. It's a CM chondrite, and it's magnetized. And if you take that meteorite and you raise its temperature, you heat it up, and you measure its magnetic field as you heat it up. As you heat it up, so on the bottom axis here, as you heat it up, the magnetization decreases. The magnetic field is lost as you heat it up. So what this means is that the parent body that Murchison came from, the asteroid that it originated on, must never, at least in the section that it's from, must never have exceeded 550 degrees Celsius. So one of what I've been working on for some of my starting research here is figuring out which asteroids would fit this bill. So for example, so these are thermal evolution models of asteroids. And so for example, if on the bottom axis is the time after the solar system forms. And so if an asteroid forms at say 2.4 million years, it comes together, and then it starts heating from that radiogenic decay. And then by the time the solar nebula dissipates at a little less than 5 million years, the asteroid's already heated up to 1,000 degrees Kelvin or more. And so this would already be well beyond what we know that these CM chondrites experienced. However, if this asteroid formed a little bit later, it would have less radiogenic elements. And so, for example, if it formed at 3.2 million years after the beginning of the solar system, and then began heating, it's not quite going to heat up enough to lose its magnetization. So what my research is about here is finding out whether we could still have these large asteroids today, which could be magnetized like for example, the CM chondrites. So I'll come back to this a little bit later. But for now, so that was the first process. The solar nebular field could magnetize these chondrites really early in the history of the solar system. But what about the magnetic fields in iron meteorites or pallasites? And so this one's actually a little bit more tricky because so we have these iron meteorites, right? But you actually you saw me, take this screwdriver, and I magnetized it really easily just by putting it next to a bar magnet. And so remember I said people go searching for meteorites with magnets? So it turns out a lot of the magnetic fields in these iron meteorites are probably contamination from being on Earth. So it's very difficult to determine magnetization in iron meteorites that we know for sure came before it landed on Earth. So that's a bit of a shame. But this doesn't stop the scientists. So there are other ways we can tell. So believe it or not, we don't measure the magnetization in the iron itself, but we look at iron within olivine grains within pallasites. And so these irons that are trapped in these minerals are not easy. You can't just easily demagnetize them or remagnetize them with a bar magnet. They're more stable. So we still have a way to study the magnetic fields that these experienced along their lifetime. And so there's a bunch of different results for these. This is sort of a new area. But some of these, based on dating the, again, the minerals within here, give ages around 100 million years after the formation of the solar system. This ranges widely, but these are certainly much later than the solar nebular field. So it's definitely not the sun that's magnetizing these guys. So what's another possible process? And what we think, so the Earth has a strong magnetic field, right? You've used a compass before. Compass is just a magnet, and it lines up with Earth's magnetic field. And Earth has a magnetic field because we think it has a a liquid iron core. And this liquid iron is moving around. You'll have to trust me on this because I'm not going to go through the physics because I don't know the physics. But the liquid iron in the core is moving around, and a conductive fluid moving generates a magnetic field. And this is called a dynamo. So the Earth is big, it's massive, and it still has a liquid core today, and it still has a dynamo running. No asteroid today would have one of these. They've all cooled down far too much. But remember, these asteroids, some of them differentiated, which means at some point they were hot enough, they did melt. And so these large early forming asteroids likely heated enough to melt iron and then form a dynamo. So they could have generated their own magnetic field during their lifetime. There are some caveats to this, though, because while the asteroid is generating its own magnetic field, in order for it to magnetize the iron, there has to be a magnetic field, and then the iron has to cool and solidify, and then it will capture that magnetic field and save it until it reaches Earth. But this only works if the asteroid solidifies from the outside in, because if you solidify from the inside out, you'll kill the core dynamo, so there will be no more magnetic field, and so everything else is just going to cool in the absence of a magnetic field, so it won't be magnetized. But if it cools from the outside in, then you would expect that these meteorites, these iron meteorites that are sourced from these differentiated asteroids, could contain remnant magnetization. There's a further caveat. We actually think that this is called the onion shell model, but an asteroid could differentiate. It could have a metallic iron core, some sort of magma, but then have primitive undifferentiated chondritic material that remains on the surface. And in this case, again, you could have a dynamo generating an internal magnetic field, but you could still have chondrites on the surface. And so these chondrites could also be magnetized by a core dynamo. All right, so that was all a bit dense, but basically, to summarize, we've got two methods that we think are magnetizing these meteorites. We've got the solar nebular field that was magnetizing things very, very early on in the history of the solar system. And then we've got core dynamos, which a little bit later, but also still pretty early in the history of the solar system. There are a couple other possible processes that could magnetize meteorites, but they're not confirmed yet. I'll briefly go over them. We've got accretional magnetism. So this kind of gets around to the magnetization problem. But let's suppose you start with grains that are magnetized. And these have to be really small grains. We're talking like a millimeter or less. And you start with them, and then they're going to come together. And when they come together, they're going to want to align themselves. Magnets like to align themselves to each other. So then this way you could build up a large magnetized object. Okay. Another possible source is shock magnetism. So if you shoot something at a very high velocity and you hit an asteroid and there's a magnetic field from anything, these shocked and heated fragments from this collision can become magnetized. So I believe there are laboratory experiments that have shown this, but we don't have, we're not certain that this has occurred or not. We don't have any examples for sure of meteorites that we think have shock magnetism. So now that I've gone over the mechanisms, and what we think is going on with these asteroids and these meteorites, I'm going to talk about getting to the question of why we haven't found a magnetized asteroid yet. So what the big reason is because we actually just haven't explored that many yet with magnetometers. We haven't measured that many. Probably the first was the Galileo mission in 1991 on its way to Jupiter, the Galileo spacecraft. It had a magnetometer, but that's because it was headed to Jupiter, where there's a strong magnetic field that's important for the science of Jupiter. But they turned on the magnetometer as they flew by an asteroid. And what they measured was the magnetic field deviated from 0. They measured something, and then it went back to normal as they flew by. And so for a long time, this was interpreted as this asteroid, Gaspra, I'm sorry if I didn't mention it, Gaspra is magnetized. However, more recent work suggests that, yes, it could be magnetized, but you can also explain this response in the absence of magnetization. You could also explain it just by a body of rock deforming the solar wind. So we're not certain if Gaspra has a magnetic field or not. Okay, more recently, on the Hayabusa 2 mission, the little mascot lander had a magnetometer. And so as it landed on the surface, got really close, touching the surface, it didn't measure any magnetic field at all. And so that suggested that there's no magnetization in the asteroid Ryugu on the decimeter scale, I believe. So, and this is a little bit, we'll have to wait for the full analysis of the samples to see if they match what they match with, but the the idea is that Ryugu matched carbonaceous chondrites that we have, and some of these carbonaceous chondrites we know are magnetized. So the fact that Ryugu isn't magnetized is not, it's interesting. So we'll have to see what types it matches. Anyway, the point is, still haven't measured an asteroid that's magnetized. That may change coming soon. So in 2026, NASA's Psyche mission is going to head over to the asteroid 16 Psyche. And we think that this asteroid could be, it could contain a lot of metal. It could be a metallic asteroid, our first metallic asteroid we've been to. And well, that would mean that it's a piece of a differentiated asteroid. And what we want to test with this is whether this asteroid once had a core dynamo. So Psyche is going to have a magnetometer, and one of its key questions is whether Psyche is a remnant exposed core of a differentiated early asteroid. And so hopefully we're going to get there, and it's going to measure some magnetic field. If not, it doesn't mean it isn't the core of an asteroid. It just means that maybe it could still be metal, it could still have formed a core dynamo and not be magnetized today. Only if it's formed a dynamo and solidified from the outside in would it be magnetized. So if we go there and it detects a magnetic field, it is likely that Psyche is a exposed core from a differentiated asteroid that formed a core dynamo. And then that would really help us explain some of these magnetized meteorites we have. Some of the other research I'm working on is what are other possibly magnetized asteroids? So yeah, metal asteroids, that could be the source for these magnetized iron and stony iron meteorites. But we also think, right, that these chondritic meteorites were being magnetized by the early solar nebular field. And so this other question I'm working on is, what other asteroids could be magnetized and still be mainly chondritic? So one of these I've been working on, 2 Pallas. It's an exceptional asteroid. It's quite large. It's like 500 kilometers in diameter. And it seems to match, spectrally, it seems to match the CM chondrites, which we know are magnetized. And so this is the best image of Pallas we have right now. But it seems to be mostly intact. It's definitely had a lot of collisions. It looks like there's lots of impacts that occurred on it. So certainly the opportunity for bodies to come off, meteorites to come off and make it to Earth. And so my question is, could Pallas be magnetized, and could you detect it with a spacecraft? Because if you went there and detected a magnetic field, that would, and if you noticed it was still, a chondritic asteroid, and you detected a magnetic field, that would be a strong indication that, well, it matches the CM chondrites, for example, and that it was magnetized by the early solar nebular field. So that would place a lot of constraints on the formation of 2 Pallas and its history. So the other work I've been researching is figuring out whether you could detect that with a spacecraft. And so what I've discovered is that if in the ideal scenario, where the entire asteroid 2 Pallas, if it formed at about 3.6 million years after the formation of the solar system, almost the entire asteroid could have been exposed at the right time to the solar nebular field. And so it could be strongly magnetized almost throughout if it was never disrupted along its history. So in this case, this plot here is formation time on the bottom axis. And on the vertical axis is the size of the object. So 2 Pallas is about 250 kilometers. I've placed my star in the wrong location. And if 2 Pallas formed at about 3.6 million years, the color indicates the maximum possible magnetic fields that you could possibly record. And so for context, 10 to the 14 to 10 to the 15 is about the lower limit of what you could detect with a spacecraft flyby. So my result here is that if this ideal process went on, and if 2 Pallas was completely magnetized, I would speculate that you might be able to detect a magnetic field if you sent a spacecraft to it. So I think moving forward, there's reasons to be sending a lot more magnetometers to asteroids. Right. So to conclude here, I think there are lots of exciting discoveries waiting for us, making magnetic measurements of asteroids. I think as we send more spacecraft with more magnetometers, it'll really help us nail down whether our formation hypotheses are correct. Really, from these magnetized meteorites, they suggest that these asteroids formed in the solar nebular field or hosted their own dynamos. And so the future measurements of magnetic fields around asteroids will really allow us to test these formation hypotheses. So with that, I will take any questions.
Well, let's thank Sam for his fine talk. I have about a dozen questions, but I'll defer for the moment, and I'll let Juliet handle any additional questions that might come up first.
So anyone can feel free to unmute themselves and ask a question, or if you prefer, you could put it in the chat. But I don't have any questions in the chat yet. Oh, we do. What will the strength of Psyche's magnetic field, if it has one, tell us?
Yes. So hold on. What will the strength of Psyche's magnetic field tell us? So, right. So this is kind of interesting because if Psyche gets there and there's a strong magnetic field and it's clear that the surface has a lot of iron on it, then that really tells us I don't want to speak too definitively here, but that really tells us that there really must have been some sort of core dynamo. The asteroid must have generated its own magnetic field, and that as it solidified, it magnetized the material as it cooled down. And so it will tell us that well, first off, it'll tell us that Psyche is a differentiated body that had a core. It's the exposed remnant, the exposed core of a protoplanet, and that it cooled from the outside in. If there's a weaker magnetic field, then explanations could get a little bit trickier, especially if you don't notice a lot of metal on the surface. If Psyche looks like it could still be primitive in some way on the surface, then this could make it a little bit more complicated. Then maybe we're not sure if the magnetic field is from a dynamo. Maybe it could be magnetization from the solar nebula, for example. But so the strength of the magnetic field is going to have to work in tandem with other measurements from the spacecraft, is I guess how I'd work with that. But certainly if there's a strong field, that's going to point to a dynamo.
Thank you. And Gary Bostrup raised his hand. So if he'd like to speak now, by all means.
Yeah, can you hear me okay, Sam?
Yes.
Okay, it goes to the fact that, first of all, I think you've only mentioned iron as a ferromagnetic material. And I'm wondering how cobalt and nickel, which are also components of meteors, would play into this. But my core question is this, in that I would think your search is going to be long and drawn out for magnetic meteors and asteroids, because they're all going through the Curie point and they're all losing their magnetic field. And so good luck, if you could address that.
Well, the thing is, though, we have these meteorites that are magnetized, and we know they were magnetized, and we know they made it to the surface, and they still have it. And we can date it, and we know that they were magnetized a long time ago in space. So
yeah, but weren't these just the fortunate few that never went through their Curie point when they got hot?
That's a good question. So that's part of the thermal modeling I did, which shows that if you form a little bit later, so the whole asteroid won't go through the Curie point. You can retain these more primitive objects, which are never going to exceed the Curie point of these various. So there's actually a couple different minerals that we look at. So in like CM chondrites, it's magnetite and pyrrhotite. They're actually even more constrained than iron. In these cases, they can't exceed. For pyrrhotite, it's like 300 degrees Celsius, 200 degrees Celsius. But if these asteroids form, if they form at the right time, they won't exceed that temperature.
Okay, so you are, with your work, you are addressing the fact that it may have more iron versus more nickel versus more cobalt, and that goes to the likelihood of finding a magnetic field.
Well, this is a little bit tricky because when I talk about these, I'm talking about the magnetic. When we've looked at these meteorites that are magnetized, we look at them and we know what's in them that's magnetized, and it's either iron or it's these iron-bearing minerals that we notice carry the magnetization. So typically it's magnetite, pyrrhotite, or just metallic iron.
Okay.
But there certainly are other minerals that can be magnetized, but they don't seem to be important for these meteorites.
Because of their quantity.
Yeah. They're typically much less.
I see. Okay, thanks.
Let me interject and ask my first series questions. You mentioned that LL chondrules have some, but of course those chondrules are probably getting their magnetization while the chondrules themselves are cooling through the Curie point prior to being accreted to the asteroid.
Yeah, absolutely. So this gets into that. Continue. Sorry.
And that's a very different situation than the magnetite and pyrrhotite formed by aqueous alteration on the parent body of the CMs.
Yes, absolutely. So in the case of these chondrules, we've got, it's actually the way we know that they're magnetized before they made it to the Earth is because these chondrules are all magnetized in different directions. So within each chondrules, they're uniformly magnetized. But then one chondrule next to a different chondrule has a different direction. And so we know that they were magnetized before they came together before they came together. And so this is, it tells us, right? So it was magnetized before the asteroid formed.
Interestingly, there's an analogy to that. The AB enstatite chondrite breccia has different class oriented in different directions as well.
Yes.
And I find that very interesting. One final question at the moment, and that is, did you see if there's check the correlation, if there is any correlation between the degree of aqueous alteration of the CMs and the intensity of the magnetic field that they've experienced?
Yeah, so I personally have not, but this, the work I cited, I think it's Cornette et al. 2015, is really the paper that shows the paleomagnetic results from these CM chondrites. And yes, I do believe they provide a discussion of the level of aqueous alteration. But the problem is there's actually they only measured, I think it's 5 or 6 different CM chondrite specimens. So I think we need to look at more. So maybe that's opportunity for a more detailed study there. But yes, there certainly should be some sort of correlation. Sorry, that doesn't definitively answer.
And let me ask one more, and then I'll hand it back to Juliet. And that is Pallas near a resonance that you might expect it to be able to contribute CM chondrites to the inner solar system?
That's outside of my expertise, but
because if it's not, then you're barking up the wrong tree, probably, because there's so many CMs.
Great point. That's a great point. I believe that was discussed in this the paper I cited, who claim that Pallas is what's the word? Spectrally similar to CM chondrites. So they're not saying it is. They're saying it's.
But if it's not near a resonance, then.
Right. The other. I actually don't know, so I'll have to check this myself because that's a great point, and I should definitely look into that because if it isn't right, that's a big problem. I know that there's the Pallas family of objects, right? There's like the asteroid Phaeton.
3200.
Yeah. Where's that guy?
That's pretty far, though, right? That goes.
Yeah. No, that's a great question. I guess I'll say I need to look into that more. So thank you for bringing it up.
Okay, go ahead, Juliet.
Yes, so we have some more questions here. How much is the original magnetism of a meteorite affected if a collector uses a magnet to find or check it?
As you know, as I can demonstrate with just my little bar magnet here, you can change it quite a lot. So you can basically how much is it affected? You're not going to be able to get any science results out of it. And so there's just really no way to be sure with these like iron meteorites at the large scale, whether they were exposed to some magnetic field on Earth. But yes, as a collector, if you use a magnet on it, yeah, you've probably ruined any magnetic field, any science value of the magnetic field in it. There are, as always, there's a caveat to this. There are these new methods. We can take like an X-ray microscope and then look at like these individual isolated grains in the iron meteorite. And we can get the direction of those because those are they're isolated and they're locked in and they're harder to change. And so there's in fact, this is like very recent work. I think it was presented at LPSC also this year. By, I think, the MIT Paleomag group.
Hi, this is Mendy Uzulu. Is it okay if I just like add a little bit to all that?
Yeah.
Go ahead, Mendy.
So Jerome, and I'm gonna mess up his last name because I've never heard it.
Checkup.
Thank you, Gattacheka. Okay, so I was gonna say it right. When I visited him in Aix-en-Provence, you know, he was doing a lot of work on I think it's paleomagnetism. And he ended up working with a company out of France for a fairly low-cost device that actually checks magnetic susceptibility. And by checking susceptibility, you don't disturb any of the paleomagnetic fields. And so he's been really trying to push for these devices to be handed out to nomads and things like that, so that, because the typical way of checking whether you have a chondrite or a chondrite or other things is just with a piece of magnet. And so there's a whole lot of science that is being destroyed. And even, you know, when there's falls and there's people going out and hunting for them, they're also using magnets because, you know, for the vast majority of people out there, that is the easiest and most accessible way to check if you have a piece of meteorite or literally road tar. So anyways, you know, the bottom line is for anyone doing magnetic science related to magnetism, if there was some way of being able to lower the cost of such devices, that would probably help tremendously.
Yeah, thanks for that. That's really neat.
And if you don't know Jerome, you should probably meet him.
Thanks.
We have a question directly related saying, are we clear that the passage of a meteorite through the Earth's magnetic field has no effect on the meteorite?
No, it also definitely could. Yeah, so that's the other thing. Especially also, right, as the meteorite entering the atmosphere, right, you can get magnetization in the fusion crust too, right, because you've got some heating going on there. And yeah, you can absolutely, the Earth's field can absolutely mess with the magnetization of these meteorites as well, but only the ones that are easily magnetized.
We often see magnetite forming in the fusion crust of these meteorites, and so obviously they would line up if they can, because they're cooling so fast.
Yes, I believe so. I haven't actually studied that, but yeah, I believe that's the case.
Another question, some are suggesting that Psyche 16 is a rubble pile asteroid, not a remnant, once melted core. Will we be able to tell from the magnetization measurements what the internal structure would be?
There's a couple of different ways to go about this. So, yeah, so if it is a rubble pile, it's going to be a strange rubble pile, because we still think it has to have a decent amount of metal in it from like radar measurements. So it's going to be a strange rubble pile if it is one. But yeah, if we detect a magnetic field from the asteroid, right, that's going to tell us a lot about what it's made from and what its past was. If we don't, there's actually still a chance, and I don't know who's working on this right now, but there's a chance you could use magnetic measurements to reveal information about the internal structure, because the solar wind is a magnetic field, and that magnetic field is going to interact with 16 Psyche. And if 16 Psyche, we think it should have a decent amount of metal in it based on our telescopic observations. And so it's going to be conductive. And what that means is it's going to amplify the solar wind. And so there's going to be some interaction of the solar wind with Psyche. And there may be a way to look at this interaction, the way it's deflecting the solar wind, and infer properties about the interior of Psyche. I'm not actually sure who's working on this at the moment, but there's a possible angle here.
Let me ask one additional question. Can you explain a little bit more detail why you think the asteroids have to crystallize from the outside in, And the reason I'm saying that is because John Wasson always believed that the irons were crystallizing from the inside out, because he thinks even if they were crystallizing from the outside in, the metal that crystallized would founder to the center, and then that would act as a nucleus, and it would crystallize from the inside out. Did you think that the magnetization of the irons rules that out?
It's a good question, and it's a tough one to answer. I cannot say, I would not have an opinion on this, a strong opinion yet. I don't know enough yet. But what I'd say is I know that, right, if it's the dynamo that's magnetizing these guys, if it starts solidifying, if it's solid in the center first, that's going to shut off the dynamo sooner. And if the dynamo shuts off and the iron on the outside is still molten, it won't acquire any magnetic field. But
the Earth has a dynamo and it has a solid inner core.
Oh, yes, correct. But it still has this convecting fluid of iron.
So why couldn't an asteroid, differentiated asteroid, crystallize from the inside out with the shell?
Solid inner core and then some conducting liquid outer core in an asteroid. That's actually a great point. And now I'm wondering why I haven't seen that discussed. So that's a good point. And
it would seem to me that that would make sense. Okay.
Right.
Go ahead, Juliet.
It may not completely rule it out.
Right.
All I know is that I believe the current work of Lindy Elkin-Stanton and Ben Weiss and the Psyche mission is I'll have to go look at their papers again, but they suggest that it has to be solidifying from the inside or from the outside in.
But
there might be some evolution.
But I think it only may be that it's a simplistic model that it shuts off the dynamo, and they are not taking account of the possibility that there's one outside a solid inner core.
You're actually okay. So then there's another idea. So there's the thermal dynamo, and then there's also the idea of like a compositional convectional dynamo. So actually this might get more at what you're talking about, where you have something solidifying and then you have these objects falling in,
stirring,
and then it's causing it to churn, and so you could get a compositional because of the objects moving through the fluid, and you've got this convection going on, you can get this compositional dynamo. And so, yes, actually, there are papers about how that could also produce a magnetic field. It would be a slightly different dynamo than the Earth has. And it would be, a thermal dynamo would have to be pretty early in the history, and a compositional dynamo would have to be later, if that makes sense.
I just want to, before people like Ed Scott jump on me, I just want to say that there are other models for the crystallizing irons, like dendrites coming in from the outside and things like that, which would be consistent with that. So I just wanted to say that things are a little more complex. Okay, I'll reserve my rest of the questions for a while. Go ahead, Juliet.
Gary has a question, so I'll let Gary ask his question or has a comment.
Yeah, thank you. You know, this may go to Alan's question as well, in that I would think if you have an asteroid with a dynamo that's active and as things cool off from the interior or the exterior, you would see shifts in the magnetic field. You know, that as each layer goes through the Curie point, you would see a shift or certain things. So if you can look at that part of the aspect of the construction of the anatomy of the asteroid, you'd be able to see all sorts of different orientations in the magnetic field, indicating how it cooled off.
This is a great point. And I think some of the recent work on trying to look at the remnant magnetization in these iron meteorites is actually trying to look at that, because we think some of these different classes of iron meteorites are coming from different stages in the cooling process. And so we want to look at, so the idea is, can we look at the magnetization of these iron meteorites and tell when the dynamo shut off or which way it was solidifying?
Precisely. Yes.
It's hard because the iron meteorites are easily messed with. Their magnetization is easily messed with when they're on Earth. So, but there's a great abstract, I think, from this LPSC that talks about this exact issue. Fortunately, I'm blanking on the name.
Well, you know what I would suggest is, sure, the magnetic field might be altered, which is north, which is south, but you might look at how the crystals are oriented in the matrix, because it's possible they would align with the magnetic field, and there's the north and south pole. But on the other hand, the magnetic field could be destroyed, but once it's gone through the Curie point, you still have the crystals intact. So maybe that's one way to see. You follow what I'm saying?
Yeah. I recommend looking. Yeah, this recent abstract in LPSC, I think, gets at some of these topics.
Mm-hmm. Okay.
Anyway, it's still very active, very recent stuff that we're trying to figure out.
Appreciate it.
So the time is running late. Juliet, we'll have one more question, not by me.
Okay. I received a question via email prior to the talk, so I'll ask that. So make sure we cover that. I wonder about whether the magnetization could be caused by impacts or fragmentation. Stuff gets stressed and sheared on impact, and permanent magnetism could result from a variety of mechanisms, moving electrons around or resetting magnetic domains. Is it possible that under some PT chemistry conditions, physical stress, strain deformation, or instantaneous currents could impart permanent magnetization during the collisions that tore these bodies apart?
Yeah, so hitting me with some more hard questions here. Again, this is a little bit outside of what I've been studying, but yeah, absolutely. And I briefly touched on it. I had like one slide for it where I bring it up that yes, it's possible. There's lab experiments that say it's possible, but we actually don't think that any of the magnetized meteorites we have were caused by this. And I don't want to be too bold and say I know this confidently, but I believe the reason is because we can look at how shocked these meteorite samples are, and then we can infer based on their degree that they've been shocked, how strong the magnetizing field would have had to have been for this to have all worked out. And it's outside what we'd expect. So it would have to have a really strong field. These samples aren't shocked enough to suggest that that was the mechanism that caused it. But it's certainly possible, and in fact, it almost seems likely, right? That seems like a pretty easy explanation for all this. So I certainly wouldn't be surprised if we find some samples that have that.
Well, Phil Bland has been advocating this for a while, I believe. And also, I should just say that some meteorites appear to have been shocked and then annealed, which makes them appear less shocked than they were initially. So that makes that perhaps more plausible.
That's absolutely possible. I hope that's not the case, because that would make my research less fun.
I think it's pretty clear it's the case. But let me ask you one final question. Then, is it possible to wash out a terrestrial field so you can get back to the other field by? Because I remember Frank Press was talking about that for some rocks that had been contaminated, some terrestrial rocks, and he could wash out some magnetic field in there to get to an original magnetic field that they experienced.
Okay, can you say that again?
Is there some way to sort of raise its temperature, perhaps, and get rid of the magnetic field that it was contaminated with to get back to the initial magnetic field it had?
What you could do is you can, so you use this, you expose it to a strong magnetic field, and you just vary that field a lot, very rapidly. And so by doing that, you'll demagnetize what you'd call the low coercivity
Right.
natural remnant magnetization. And so you'll erase that, but the high coercivity stuff, the stuff that's more stable, the stuff that could have lasted longer, would be preserved.
In different phases, presumably.
Yeah.
Okay. And anyway, there's a lot more we could talk about, and other people did, but time is a little late now. So I want to thank Sam.
So
I want to thank you. It was a fine talk and interesting discussion afterwards. So let's thank everyone.